Hey guys, Luke here again, and I'm here to talk about how we're going to make our CLI bonds, or carbon lithium bonds, or R-Li bonds. In this first case, we're going to be talking about the Shapiro reaction, which is a very important reaction in this course that I'm currently doing at university. Touch wood, okay at the mechanism. The mechanism's not too bad. You need to remember to add 2 equivalents of butyl lithium, and there's a few reagents to remember as well. But the first step, we start with a condensation reaction, which in our case, we didn't have to remember how to do a condensation reaction. We should know how to do it from previous years, but we don't have to remember how to do it, I don't think, for this exam. I'm going to try and talk you through it anyway for my help as well as yours if you've not seen a condensation reaction before. Fortunately, I've not got a pen, so we're just going to do it with my finger. So you need the amino group, or amine group should I say, with NH2 group there, and we need a ketone. We'll call this group here the R group, and obviously this group here is effectively, we'll call it in inverted commas, a protecting group sort of thing. It's just something we've got to remove eventually in this reaction. So the nitrogen attacks there. I've done the first step already. The nitrogen attacks and pushes the electrons onto the oxygen. The nitrogen then forms a bond here. Nitrogen, it's got 2 hydrogens on it, and the R group. We go through a proton transfer because the nitrogen is positively charged, it's 4 coordinated, and that goes on to the oxygen. The OH group now gets protonated to form OH2 here, and the OH2 can come down and break the bond here, and because this is a single bond now after we've done this attack, and form a double bond between the carbon and nitrogen. And obviously now we've got a nitrogen that's 4 coordinate again, because we've got a double bond here, a positive charge, and the R group. The R group, the H just effectively gets it just gets deprotonated the nitrogen, so we just remove the H by adding a base to form this product here. So what we do from here is we effectively just add our butyl lithium bonds, our butyl lithium. This adds first off to the nitrogen, and then adds to the carbon there, and this is due to internal heteroatom, which directs the deprotonation or lithiation. Effectively, I don't think it will matter which lithium you add first, but if you can't remember exactly, just add them, make sure to add 2, basically. Once you've added this lithium, anyway, we lose it straight away anyway, as this effectively goes all the way up here in order to remove our SO2 group, which I said was a protecting group. It's not really a protecting group, it's just a group that we can remove. The second lithium can then give its electrons to the dinitrogen here, which can then break the bond between the carbon and the nitrogen, and then we reform the bond between the lithium and the carbon. And the driving force for that part of the reaction is that we're making N2 gas, and obviously the dinitrogen molecule is the strongest bond in the world, the NN triple bond. And then it's pretty much the same as what we had in the last video where we did the halogen lithium exchanges. The lithium can then attack a aldehyde and obviously move the electrons onto the oxygen of this aldehyde, attacks in the least sterically hindered position again, and once that happens we form this product here on acid workup. So the dilithio intermediate, which is this here, can be alkylated due to heteroatoms in close range. So as I said earlier, I think I said anyway, or I said in one take of this recording, that there's a stabilization factor between these 2 atoms there, and effectively that can attack the R. So what we've got, we start with this, we have the lithium, we've got the interaction there, but the lithium does the same. Sorry, my bad. The lithium attacks here, we form R-Li, The butyl lithium attacks again, comes again and forms R-Li here. And then we've still got the R group. So instead of, we still get rid of N2 gas. We've got an R group now instead. And then we add Me3SiCl to displace our lithium. That's pretty much it for that. Now making R-Li bonds by direct deprotonation and Schlosser's bases, which you just saw there, we'll come on to later. What have we got here? We've got a we've got an ester there, a carboxylic acid, something, an ester. I think we've got an ester there. We'll roll with it. But it doesn't matter about that. What we do is use NaH, which attacks oxygen, or the oxygen attacks the Na, should I say, to form a single bond. Well, okay, let's go through this. H attacks up there, and then the oxygen can attack the Na to get ONA. It's kind of like forming OH. We've lost the hydrogen there, form the double bond here. We added butyl lithium again. This is a strong base. This whole thing is, using butyl lithium. We're getting used to it, the use of it now. But pKa values are good to remember. This is pKa 11, pKa 25, which means it can undergo this reaction. This is pKa 30. We need a stronger base than pKa 30. pKa 42 this. And then, obviously, it is an ester because we've got C, double bond O, and then O, ET there. And basically we just attack the the double bond O to form OLI, and then from there we can do pretty much what we did on the last page, in the last section, where we add RX, and that reforms the double bond O and removes the double bonds that we formed there. And pretty much I think that's pretty much the reaction done. Not very well explained, I know, but if you just remember the general scheme of the reaction, I think it'd be good to go. That's my case anyway. That's what I'm going to try and do. Like I said, organic chemistry is not my forte really, so I'm just going to try and work with what I've got. Next time we're going to try and talk about some more lithium compounds, I believe, and yeah, that's pretty much everything. Thanks for watching, guys.